The lesson objectives. Geostationary orbit, uses of geostationary satellites, and then 5.4.4 gravitational potential and energy. Gravitational potential at a point as the work done in bringing unit mass from infinity to the point. Gravitational potential is 0 at infinity. Gravitational potential Vg is equal to minus gm over r at a distance r from a point mass m. Changes in gravitational potential. Force distance graph for a point or spherical mass. Work done is area on the graph. Gravitational potential energy is E is equal to m times gravitational potential, and that is equal to minus gm small m over r at a distance r from a point mass m. Escape velocity. Alright, so a satellite is an object that is orbiting a planet. So in this case, there could be artificial satellites or natural satellites. So for a geosynchronous orbit, it is a high. If this object was in the geosynchronous orbits, then it will be in a high Earth orbit, and that will have the same angular velocity because it has to match the Earth's rotation. It is located at around about 36,000 kilometers to two significant figures above the Earth's equator. Now, a geostationary satellite is always above the Earth's equator. There's a difference between geosynchronous and geostationary, because if you look at the bottom here, it says geosynchronous satellites can have any inclination, but geostationary has to be above the equator. So for a geosynchronous orbit, this position is a valuable spot for monitoring weather, communications, and surveillance. So the period is exactly 1 day, and it remains constantly above 1 point on the Earth's surface. So if you look at the diagrams, geosynchronous orbits can be in any inclination. So if you look at the middle one is around the equator, but if you look at the left and the right, the one on the left is orbiting around the poles, and the third one is at an inclination, 45 degrees. Right, so what are the properties of a geostationary satellite then? So A, they have an orbit which lies in the same plane as the equator of the Earth. It is directly above the equator. They remain above a fixed point on the Earth's surface. B, the period of the Earth is exactly 1 Earth day, 24 hours, roughly. C, they have the same angular velocity as the Earth, because it has to move with the Earth. So if it moves with the Earth, it will have the same angular velocity. They move around their orbit in the same direction as the rotation of the Earth. Okay, so geostationary orbits fall in the same category as geosynchronous, but it is above the equator. This one special quality makes it unique from geosynchronous orbits. So geostationary satellites are geosynchronous, but geosynchronous orbits aren't necessarily geostationary. Alright, so what do you use them for? Okay, so geostationary satellites or geosynchronous satellites, they are used to send TV and telephone signals. You don't need to alter the angle of the receiver because it moves with the Earth. The satellite moves with the Earth. It can track weather. But the disadvantage is that it is expensive. Another disadvantage is that the satellite could fall towards the Earth, and if you have too many of them, it can be crowded. Hence, it's called space junk. Alright, what is gravitational potential? It's quite similar to electric potential because electric potential is energy per unit charge. For gravitational potential, it is defined as the work done per unit mass in bringing a test mass from infinity to a point away from the object creating the gravitational field. So if you look at the diagram, by definition, if it's from infinity, then there is no work done because infinity is very far away from the planet, and because it is so far away, the gravitational field doesn't affect the mass. However, what happens when you bring that mass that was from infinity close towards the Earth? When that happens, that object is in the gravitational field, and so there is energy there needed to move from that point towards the planet. In this case, it will be negative because you are not doing any work. It is the field that is doing the work because the field is attractive. All right, so if you remember Newton's law of gravitation, F is equal to G m, big M times small m over r squared. Now, big M can just mean m1 and small m could mean m2. Because of the definition, because of the definition of gravitational potential, which is energy per unit mass, how do you work out energy? Well, energy is work done, which is the same as force times distance. So if you times distance in the force equation, one of the r's will go, and because it's per mass, you divide by m. So you times by r and you divide by m, you end up with v is equal to minus g times m divided by r. Now if you look at the graph of gravitational potential against r, you get that curve in the negative region. And if you remember electric potential is energy per charge. So it is like electric potential, and it is defined as the work done per unit mass taking a small test mass from zero potential. Remember, zero potential is from infinity to any point P in the gravitational field of the planet. Now, the reason it has to be negative is because you would need to do work pushing the mass away from the planet to infinity. The reason it has to be negative is that you would do work pushing the mass away from the planet to infinity. Okay, so that just means that in order to move away from the gravitational field, you need to do work in bringing that mass away from that planet. However, because you bring it towards the planet, it is negative because it's attractive. Right, so this is just the mathematical steps. So you times both sides by r, and then in the yellow box in the center, that's the equation for work done or energy, and then once you divide that by m, you end up with gravitational potential is minus g times m over r. Right, let's have a look at a few examples of gravitational potential. I'm looking at the right hand side towards the bottom. So what happens when it is 10,000 kilometers away from the center of the Earth? Well, using the equation v is equal to minus g m over r, remember that r is the distance from the center of the planet to the point, just to any point. So if it's 10,000 kilometers away from the center of the Earth, the r, you would have to add on the radius of the Earth. And the radius of the Earth, let's just say it is 6,371,000 meters. So for r, you need to add on 10,000 plus the radius of the Earth. Putting the numbers in, you end up with 24.44 megajoules. Now it has to be negative. So what that means is that when it's at 10,000 kilometers, for every kilogram, you need to use up 24.44 megajoules away from the center of the Earth. Right, so how do you calculate the work done needed to go from one potential to another? So the change in potential, so remember the equation for potential is on the left hand side, V equals minus G times M divided by R. Now if you are at a different distance, then there will be different R's. So that's why you have change in potential is equal to minus G times M brackets 1 over R1 minus 1 over R2, because you are at different distances, and when you are at different distances, you are at different potentials according to the equation. Now what is this equation? This is the change in potential energy, which is the change in work done, and because the equation for gravitational potential is gravitational energy divided by unit mass, you just times by the mass to the change in potential. So the change in potential times mass will give you the change in energy. Graphically, let's have a look at this. So on the left hand side, on the y-axis, It is the force needed to move 1 kilogram in newtons, and on the x-axis you have the distance away from the planet. And the area under that graph will be work done. If you know integration, you can integrate the force with respect to r with the limits b and a, and then you would get this equation.
Now, the definition for escape velocity is defined as the velocity needed for an object that has enough kinetic energy to escape a gravitational field. Now, let me draw a planet. So let's draw a planet. And let's just say from here to here is infinity. Okay, so by definition, the gravitational potential is equal to 0. And then it becomes more and more negative. So from here all the way down to the left-hand side, it becomes more negative. Okay, so why is it negative? Now, because you are not doing any work in bringing an object from here to the left, towards the planet. Because the gravitational attraction is always positive. So you're not doing any work in bringing an object from infinity towards the planet because the gravitational field is attractive. However, let's just say that you're moving a book away from the center of the earth. You're doing positive work. So you're doing work against gravity. You're doing work against the gravitational field. So that's why it is negative towards the planet, and it is positive away from the planet, because you need to do work in order to escape the gravitational field. All right, so let's write down the formula for gravitational potential. You know that the gravitational potential is energy per unit mass, but you know that the force, using Newton's law of gravitation, the magnitude of the force is gm1m2 over r squared. And if you times both sides by r, you get the energy is equal to gm1m2 over r. So that's the work done, or energy. And then if you have the potential, now the symbol for potential is V. It is similar to electric potential. So if you divide by m, you get the gravitational potential is equal to energy divided by mass. And so if you divide one of the m's, you get, was actually minus m minus g m over r. Let's put minus here. The minus just means that, so in this case, it is negative going towards the planet. So it's negative towards the planet. Here it is more negative towards the planet. If you remember the electric potential is like voltage. I mean, it's the same. Then voltage is energy per unit charge. If you remember, V is equal to kQ over R. That's electric potential. The top is gravitational potential. Okay, so if we go back to escape velocity, it is the minimum velocity needed to escape the Earth's gravitational field. Now let's use the conservation of energy. So let's just say that you want to escape the planet, but you need a certain kinetic energy. Now the equation for kinetic energy is half mv squared. And what is the gravitational potential energy? Well, not mgh in this case, because mgh is only if it's a uniform field. But assuming that the field is not uniform, then you need to use this one. And let's just take the magnitude of that. So half mv squared is equal to gm1m2 over r. Divide both sides by m, and then times both sides by 2 square rooted. You end up with V is equal to 2 gm over r.